Yes, the history of the Second World War were a gallery of machines. The section reserved for prototypes that never saw combat would be a room of giants, oversized, over-engineered, and overburdened by ambition. It would contain hulking shapes of steel that promised invulnerability, vehicles that could have rewritten tactics if only they had reached the front, and experimental contraptions that strained the boundaries of what factories, engines, and logistics could deliver. In that gallery, every prototype is both a dream and a confession, a dream of battlefield dominance and a confession of what designers and generals feared most. During the war, all major powers experimented with advanced armored vehicles beyond what was deployed in the field. Some sought unstoppable breakthrough machines, others aimed at perfecting mobility, others at combining roles into one multi-purpose chassis. But time and again, practical limits, mechanical reliability, transport, fuel, and cost drew a hard line between what could be imagined and what could actually fight. Understanding why these land-based prototypes failed to reach combat tells us more about the inner logic of wartime engineering than any victory parade could. Let's explore these land prototypes by looking at the cultures of innovation behind them, the specific machines that embodied the extremes, and the systemic reasons they never fired in anger. The ambition behind steel behemoths. By 1942, every major army had learned a simple but brutal lesson. Armor and firepower were never enough on their own. The early war triumphs of fast, lightly armored tanks had given way to a new obsession with protection and hitting power. The result was a race to design heavier, more heavily armed, and more complex vehicles. For Germany, which had built its military mythology around decisive technological superiority, this meant a relentless pursuit of the ultimate tank, the one that could destroy any enemy vehicle while being immune to return fire. The result was the creation of colossal prototypes like the Maus, the E-100, and even paper designs like the Rata, an almost surreal 1,000-ton land battleship that existed only in concept sketches. In Britain and the United States, the logic was different but related. Both nations sought specialized vehicles to solve battlefield problems. The British focused on assault tanks that could breach fortifications and survive heavy anti-tank fire. The Americans explored tank destroyers and super-heavy prototypes meant to crack defenses like the Siegfried Line. The Soviets, meanwhile, balanced grand prototypes with their principle of simplicity, favoring mass-producible designs like the T-34 and IS-2, but never resisting the temptation to test gigantic armor projects on the side. Across all these nations, the pattern was consistent. Whenever a war dragged on and casualties mounted, engineers reached for technological miracles. They wanted machines that could substitute for numbers, morale, or time. But the battlefield, like physics, is unforgiving. The Maus, monument to excess. The Maus remains the archetype of a tank that was too big to fight. Designed under Ferdinand Porsche's leadership and approved by Hitler himself, it was intended to be the last word in armored warfare. A tank so large and powerful that nothing on Earth could destroy it. It weighed roughly 188 tons, almost 3 times heavier than the already massive Tiger II. Its armor, up to 240 millimeters thick, could, in theory, resist any Allied anti-tank shell. Its main gun, a 128mm KWK-44, was capable of destroying any enemy tank at extreme range. On paper, it was an engineering triumph, a masterpiece of overprotection and overkill. In reality, the Maus was a tragedy of impractical design. Its sheer weight made it nearly immobile outside perfectly firm ground. It crushed roads, collapsed bridges, and demanded specialized railway wagons to move. Its Maybach engine, even with modifications, couldn't deliver the necessary torque, limiting it to crawling speeds of less than 13 kilometers per hour. To supply fuel for just one Maus, several trucks had to be dedicated exclusively to refueling it, a logistical absurdity in late-war Germany. 2 prototypes were built. One ran under its own power during testing at Böblingen. Another was incomplete when Soviet troops captured it in 1945. The Soviets later assembled a hybrid using the parts of both and took it to Kubinka for testing. They admired the engineering, but immediately recognized its futility. The mouse could neither exploit breakthroughs nor retreat quickly, and it was far too expensive to produce in numbers that mattered. In strategic terms, the mouse symbolized Germany's late-war desperation and the collapse of rational resource allocation. While thousands of medium tanks could have been built for the same cost and labor, the Reich pursued a mechanical fantasy, a single tank to reverse a lost war. The mouse, then, was not a failure of engineering alone, but a failure of strategic imagination, a belief that technology could replace strategy. The British tortoise, the fortress on tracks. On the other side of the Channel, the British Army was wrestling with a different set of anxieties. The D-Day landings and the push into Europe meant facing heavy fortifications and entrenched positions. For this, the British sought a vehicle that could advance methodically through defensive belts, shrug off direct hits, and deliver heavy fire on bunkers and pillboxes. The result was the A-39 Tortoise, an enormous assault tank that resembled a mobile bunker. The Tortoise weighed around 80 tons and mounted a powerful 94mm gun in a fixed casemate. It had thick frontal armor and a low, boxy silhouette designed for direct assaults. Only 6 prototypes were built, and though some reached testing stages, the war ended before they could see combat. The Tortoise reflected British engineering pragmatism. It was mechanically reliable for its size, and its gun was effective, but its operational limitations were obvious. Transporting it across Europe required dismantling infrastructure, its speed barely exceeded 12 kilometers per hour, and its turning radius was enormous. Once deployed, it could dominate a small sector, but redeploying it quickly was nearly impossible. In essence, it was a perfect machine for a kind of static, siege-style warfare that no longer existed by 1945. Still, the Tortoise program yielded valuable data. Its suspension design, heavy armor construction, and internal layout informed post-war development of British heavy armor. Like many prototypes that never fought, it was a laboratory, a proof of concept that pushed design limits, even if it arrived too late for battle. The American T-28/T-95, the super heavy tank destroyer. In the United States, the development of the T-28, later reclassified as the T-95 gun motor carriage, was driven by fears of encountering massive German fortifications or enemy heavy tanks in Europe. The U.S. Army wanted a vehicle that could breach the Siegfried Line and withstand heavy fire. The result was a 95-ton tank destroyer armed with a 105mm gun. Its frontal armor was an extraordinary 300mm thick, more than enough to resist any known German gun, but it lacked a rotating turret, relying instead on the entire chassis to aim horizontally. To distribute its weight, it had a 4-track system, 2 tracks per side that could be detached for transport. Only 2 prototypes were built, and neither saw combat. The T-28/T-95 faced the same logistical problems as the Mouse and Tortoise. It was too heavy for bridges, too slow for mobile warfare, and too cumbersome to deploy effectively. By the time it was ready, Germany had already fallen, and the war in the Pacific was shifting toward mobility and air power. In the field, it would have been a liability rather than an asset. However, like its British counterpart, the T-28 offered lessons in armor casting, suspension design, and track distribution. Its testing influenced future American approaches to heavy armor, even if the super-heavy concept itself was abandoned. The Soviet approach, ambition tempered by realism. Unlike their Western and German counterparts, Soviet designers maintained a more disciplined relationship with the concept of the supertank. Soviet industry emphasized quantity, simplicity, and field repairability. Tanks like the T-34 and KV-1 embodied this philosophy. Not perfect machines, but robust, effective, and easy to produce en masse. Nevertheless, even the USSR entertained heavy prototypes like the KV-5, IS-7, and experimental multi-turreted designs earlier in the war. The KV-5, designed in 1941, was meant to carry a 107mm gun and weigh around 100 tons, a direct response to German heavy tanks. But the rapid German advance toward Leningrad forced evacuation of factories, halting the program. The concept was abandoned as impractical under wartime conditions. Post-war, the IS-7 represented the peak of Soviet heavy tank development, a massive 68-ton machine with thick armor and a powerful 130mm gun. Though technically impressive, it was expensive, heavy, and required extensive logistical support. In 1948, after testing, the program was canceled. Soviet military philosophy had evolved. Rather than relying on monsters, they invested in more mobile, versatile designs that could be produced in the tens of thousands. This pragmatism gave Soviet armored forces a long-term advantage. While Western designers were tempted by prototypes, Soviet engineers built workhorses. The legacy of this mindset would echo through the Cold War. Engineering lessons from the ground up. What do all these prototypes, the Mouse, Tortoise, T-28, KV-5, have in common? Beyond their weight and impracticality, they each expose the hidden web of constraints that define wartime engineering. 1. Power-to-weight ratio. Engines of the 1940s had limits. Most were derived from aircraft engines or adapted from smaller tank designs. Even the best power plants struggled to move 100-ton vehicles efficiently. Overheating, gear failures, and poor fuel economy plagued every super heavy tank project. No matter how thick the armor or how big the gun, a vehicle that couldn't maneuver was strategically inert. 2. Mobility versus protection. Every kilogram of armor added exponentially increased strain on tracks, suspensions, and transmissions. Designers could create vehicles immune to most weapons, but they couldn't make them fast enough to exploit that advantage. In modern military terms, protection without maneuver is death. 3. Production efficiency. Prototypes that consumed hundreds of man-hours per unit simply couldn't be built in wartime quantities. Every Mouse that might have rolled off a line would have cost dozens of Panzer IVs, tanks that could actually fight. The same logic held for every nation. Volume mattered more than perfection. 4. Maintenance and logistics. Heavy vehicles required specialized cranes, oversized transport, and unique parts. Field workshops were not equipped to repair 180-ton monsters. In combat zones where supply lines were under constant threat, maintaining such vehicles would have been impossible. 5. Strategic obsolescence. By 1944, the nature of warfare had shifted. Air power dominated, precision bombing improved, and mobility became king. Static siege vehicles designed for trench-like assaults were relics of a war that no longer existed. The super heavy tank, like the Fortress, was obsolete the moment it was built.
Beyond the battlefield, symbolism and psychology. There's another layer to these prototypes, their symbolic function. Massive machines like the Mouse or the Tortoise were political statements as much as military ones. They represented strength, defiance, and technological prowess. For leaders like Hitler, they were propaganda tools, proof that Germany could still produce miracle weapons that would turn the tide. For Allied engineers, they were symbols of determination and industrial superiority. In this sense, prototypes that never saw combat still fought psychological battles. They embodied the technological optimism of an era that believed engineering could solve any problem, even strategic collapse. And yet their fate, rusting hulls, disassembled parts, abandoned factories, reflected the limits of that belief. The human scale of steel. It's easy to discuss these machines as statistics, tons, millimeters, horsepower, but each prototype also reflected human labor and suffering. Thousands of workers built them under harsh wartime conditions. Resources diverted to them meant fewer trucks, rifles, or medium tanks for the front. When a Mouse prototype sat idle in a test facility, it wasn't just a failed weapon. It was a monument to misallocated effort in a desperate time. The crews who would have operated such machines also mattered. Imagine being a driver in a 180-ton tank with almost no visibility, deafened by the engine, isolated by armor thicker than a house wall. Many prototypes ignored ergonomics entirely. Inside the Mouse, for instance, crew space was so limited and claustrophobic that heat and fumes made long operations unbearable. The invulnerable tank could kill its crew without ever meeting an enemy. Lessons written in steel. If we step back, the pattern becomes clear. Every heavy prototype that failed in World War II teaches a version of the same lesson. Technology cannot defy logistics, and ambition cannot replace strategy. The war rewarded designs that were reliable, repairable, and mass-producible, not those that were perfect. The true innovations that changed armored warfare weren't the 180-ton giants, but the humble evolutions: better suspensions, sloped armor, diesel engines, modular components. These small iterative improvements multiplied across thousands of tanks, and that, not any prototype, decided the outcome. Still, the fascination endures. Museums around the world display surviving prototypes like the mouse, and visitors stand in awe at their size. They represent the extremes of human engineering, both its genius and its blindness. They remind us that even in total war, imagination often runs faster than reason. War in the air during World War II was brutal, fast, and deeply experimental. The skies became a laboratory where the limits of human ingenuity were tested and often exceeded. Every major nation poured enormous resources into designing aircraft that could outfly, outfight, and outthink the enemy. Yet while some designs became legends, the P-51 Mustang, the Spitfire, the Me-269, others never left the ground. They remained prototypes, test articles, or ambitious ideas on a drawing board, canceled just before they could prove their worth or failure. These are the forgotten birds of war, the aircraft that might have changed history, but instead vanished into its shadows.
The German dream of the future sky. No country produced as many ambitious prototypes during the war as Nazi Germany. The Reich's desperate search for wonder weapons extended into the clouds, creating machines that looked more like visions of the 21st century than the 1940s. Take the Horten Ho-229, for example, a flying wing bomber developed by brothers Reimar and Walter Horten. Its smooth, tailless design and twin jet engines made it look decades ahead of its time. The Horten's aerodynamic efficiency was astonishing. Its radar cross-section was so small that modern engineers have speculated it could have been the world's first stealth aircraft. It flew in late 1944, powered by two Junkers Jumo 004 engines, the same ones used in the Me-262 jet fighter. In testing, it reached speeds of nearly 600 miles per hour. But by the time the Horten was ready for mass production, Germany's war machine was collapsing. Allied bombing had crippled the factories that could have built it, and fuel shortages meant few test flights could even take place. When American forces captured the prototype in 1945, they couldn't believe their eyes. It was unlike anything they had. The aircraft now rests, still incomplete, in the Smithsonian's archives, a ghost of what could have been. The Messerschmitt Me-262, the world's first operational jet fighter, is often remembered as a revolutionary aircraft, but few remember that it was part of a much broader family of prototypes. One of them was the Messerschmitt Me-262 HG-3, a high-speed development designed to reach over 600 miles per hour with a pressurized cockpit and swept wings. It was to be Germany's ultimate interceptor, meant to strike American bombers before they could reach the Ruhr. Yet not a single production model was finished. The Allies were closing in, and resources for such advanced projects simply didn't exist anymore. Another forgotten masterpiece was the Messerschmitt P-1101, a variable sweep-wing jet that could literally change its wing angle depending on the flight profile. The design was so advanced that when American forces captured it, it directly inspired the Bell X-5, the first American variable geometry research aircraft. In other words, a German prototype that never flew influenced post-war U.S. jet development more than any combat plane ever could. And then there was the Blohm+Voss P-212, an unusual jet fighter with a tailless design and swept wings that might have become a deadly opponent if the war had lasted a few months longer. The Luftwaffe's engineers had moved far beyond the piston engine era. They were already dreaming of supersonic flight, and some of their designs on paper came eerily close to it. America's experiments, power without purpose. Across the Atlantic, the United States entered the war later with massive industrial capacity and a keen interest in innovation. While many of America's prototypes were practical and production-ready, others were bold experiments that didn't quite fit the wartime urgency. Consider the XP-55 Ascender, a radical pusher fighter designed by Curtiss Wright. Its engine was mounted behind the pilot, and it used a canard configuration, with small forewings instead of a tailplane.
It looked like something from a 1950s sci-fi comic, but during testing, the XP-55 revealed serious stability problems. It could spin out of control and was difficult to recover. Only 3 were built, and while the idea was fascinating, it was far too dangerous for combat pilots. Another oddity was the XP-56 Black Bullet, designed by Northrop. Made almost entirely of magnesium, it was a flying wing with a pusher propeller and no tail. Its futuristic shape promised incredible speed and efficiency, but again, instability and engine troubles doomed it. The aircraft barely flew before the project was canceled. Ironically, the same Jack Northrop who designed the XP-56 would later build the YB-49 flying wing after the war, the direct ancestor of today's B-2 Spirit stealth bomber. In that sense, even failures left a legacy.
Then there was the Lockheed XP-58 Chain Lightning, an oversized derivative of the P-38. It was designed as a high-altitude bomber destroyer, armed to the teeth and powered by twin Allison engines with turbochargers. Yet it was too heavy, too complex, and arrived too late. The XP-58 never went into production because by the time it was ready, the air war had already changed. America didn't need specialized bomber destroyers anymore. Even more daring was the Republic XP-72, an attempt to make the fastest piston engine fighter ever built. It used a massive 28-cylinder radial engine capable of producing over 3,500 horsepower and could reach speeds above 480 miles per hour, an incredible figure for a prop-driven aircraft. It flew beautifully, but the introduction of jet technology made it obsolete before it could even enter mass production. The Soviet approach, bold, brutal, and often secret. The Soviet Union's aviation industry was both creative and chaotic during the war. Resources were limited, yet Soviet designers constantly experimented with unconventional ideas. Many prototypes were lost to time or secrecy, but some still stand as examples of remarkable innovation. One of the most interesting was the WWII, a rocket-powered interceptor developed by Bereznik and Isayev in 1942. It was built to defend cities against German bombers with unmatched climb speed, reaching altitudes of 10,000 feet in just seconds. But the engine burned through fuel so quickly that it could fly for less than 2 minutes. One test flight ended in disaster when the rocket engine exploded mid-air, killing the pilot. The project was quietly shelved, but its technology would later influence post-war rocket and jet research. Then there was the Polikarpov I-185, a high-performance fighter that could have rivaled the German FW-190. It featured a powerful radial engine and excellent maneuverability. Test pilots loved it, calling it the best Soviet fighter never built. But Stalin's government chose to prioritize existing models like the La-5 and Yak-9, which were already in production and easier to manufacture. The I-185 never entered service, even though it was arguably superior to anything the Soviets had at the time. Soviet engineers also explored jet propulsion surprisingly early. The MiG-9 project was conceived during the war, using captured German jet engines as inspiration. While it never flew in time to see combat, its design led directly to the MiG-15, one of the most famous jet fighters of the early Cold War. And then there were experimental heavy bombers, like the PE-8 derivatives that attempted to combine piston and turbojet engines in hybrid configuration. None were mass-produced, but they represented the Soviet determination to leap into the jet age before the war was even over. Britain's secret sky. Britain's aviation legacy during the war is usually defined by the Spitfire and the Lancaster. Yet behind those icons was a network of secret projects that pushed the boundaries of what was possible. One of the most striking examples was the Miles M52, a supersonic research aircraft that could have broken the sound barrier years before Chuck Yeager's Bell X-1. Designed in 1943, the M52 featured a streamlined fuselage, rocket-powered engines, and an all-moving tailplane, a design element later essential to supersonic flight. The British government canceled the project in 1946, partly due to cost and secrecy, and partly because they had begun sharing information with the Americans. Many of its innovations appeared almost mysteriously in U.S. designs soon after. The de Havilland Vampire, Britain's first operational jet fighter, came from a long line of prototypes that started during the war, but few remember its strange predecessor, the Gloucester E-2839, the first British jet to fly. It was tiny, experimental, and built almost as a proof of concept. Without it, the entire jet revolution might have been delayed. Britain also experimented with rocket-assisted interceptors, twin fuselage designs, and even flying discs, though most remained only sketches in secret archives. The war drove innovation, but bureaucracy and budget often killed it. The Royal Air Force needed proven designs, not experiments, and that meant many revolutionary ideas stayed on the ground.
Japan's desperate skies. Japan's aviation industry faced a tragic paradox. Some of the most creative engineers in the world worked with some of the poorest resources. As the war turned against them, Japan began experimenting with increasingly desperate designs, from suicide rockets to jet-powered interceptors, most of which never reached combat. The Nakajima Kikka, for instance, was Japan's first jet aircraft directly inspired by the German Me-262. Engineers received blueprints and engine parts from Germany, but due to material shortages and bombing raids, they had to improvise. The Kikka was smaller and underpowered, flying only once before the war ended. Even more ambitious was the Kyushu J-70W Shinden, a canard-style interceptor with the engine at the rear and the wings swept forward. It was designed to climb fast and intercept American B-29s. Test pilots reported that it handled surprisingly well, but it flew only once before Japan's surrender. The J-7W remains one of the most futuristic piston fighters ever built, looking more like something from the jet age than 1945. Other bizarre designs included the Mitsubishi K-200, a rocket-powered interceptor based on the German Me-163 Comet, and the Oka suicide rocket plane, piloted by young men with almost no chance of return. These last-ditch efforts reflected not technological genius, but desperation. Still, they reveal a powerful truth. By the end of the war, every nation was looking toward the jet and the rocket as the future of flight, even if most of those machines never saw the light of combat. The legacy of failure. Many of these aircraft were failures, unstable, dangerous, or simply too late. But to call them failures misses the point. They were stepping stones. Each prototype, each engine test, each crash landing contributed something to the evolution of flight. The jet age was born from these mistakes. The Germans gave the world the first jets and flying wings. The Americans learned to control power and stability. The Soviets perfected mass production of advanced designs. The British cracked the supersonic barrier. And Japan, despite defeat, left behind lessons in compact design and aerodynamics that would influence post-war aviation. If we could see them all together, the Horton 29, the XP-55, the J-70W Shinden, the I-185, lined up on a single runway, we'd see not a collection of failures, but a bridge from the age of canvas and piston engines to the world of stealth bombers and space planes. They never fought, they never bombed or shot down an enemy, but they changed the way humanity looked at the sky. Germany's steel fantasies, from genius to madness. No nation poured more imagination into its armored experiments than Nazi Germany. By 1944, the German war industry had shifted from practical warfare to a feverish search for miracle weapons. The result was a collection of vehicles so massive, so complex, that they bordered on science fiction. The most infamous of them all was the Panzer VIII Maus, a super-heavy tank designed by Ferdinand Porsche. Weighing nearly 190 tons, it was the heaviest tank ever built. To put that into perspective, the Maus weighed as much as 10 Sherman tanks combined. Its armor was 240 millimeters thick at the front, making it virtually invulnerable to any Allied gun of the time. Its 128 millimeter main gun could destroy any tank in existence at extreme range. But there was one small problem. It could barely move. The mouse was so heavy that no bridge could carry it. It consumed absurd amounts of fuel, and even its massive engine struggled to push it past 12 miles per hour. Two prototypes were completed and tested near Kummersdorf. When Soviet troops captured the test site, they found the wrecks of these behemoths, a broken promise of unstoppable power.
The mouse was not alone. Its even more insane cousin was the Landkreuzer P-1000 Rata, a proposed tank so huge it defies belief. 1,000 tons in weight, 35 meters long, armed with two 280mm naval guns taken from a battleship. It was, quite literally, a land battleship. It would have required a crew of over 20 men and burned hundreds of gallons of fuel per hour. The project was approved by Hitler himself, but canceled before construction began when engineers realized it would be a logistical nightmare. It couldn't cross bridges, railroads, or even most roads. And then, as if that wasn't enough, there was an even larger design, the P-1500 Monster. It wasn't really a tank, but a mobile artillery platform carrying the Schwerer Gustav 800mm gun, the largest cannon ever built. The idea was to mount it on tracks and make it self-propelled. It would have weighed 1,500 tons and required its own supply train. The project never went beyond paper, but it showed how far the German obsession with size and firepower had gone. Not all prototypes were absurd. Some were simply ahead of their time. The E-series of tanks, for example, was a late-war German attempt to simplify production while improving performance. The E-50 Standard Panzer was meant to replace the Panther, while the E-75 would replace the Tiger II. These tanks featured modular parts, sloped armor, and advanced suspensions. Had the war continued another year, the E-series might have become a realistic next generation of armored warfare. There were also fascinating light designs, like the Aufklärungspanzer Panther, a reconnaissance version of the Panther with a 20mm autocannon and a low profile. Only prototypes were built before the war ended. And then there was the Kugelpanzer, a tiny one-man spherical tank found by the Soviets in Manchuria. Its purpose remains a mystery even today, perhaps a reconnaissance pod or a mobile observation post. Germany's prototypes reveal both brilliance and desperation. The engineers had unmatched creativity, but their nation had lost sight of reality. While German soldiers fought and starved, their factories built monsters that never saw the battlefield. The Soviet experiment, simplicity meets ambition. On the opposite side of Europe, Soviet engineers were following a very different path. For the Red Army, reliability was everything. A tank that could be repaired in a muddy field was worth more than a complex masterpiece that broke after a week. Yet even in that pragmatic system, Soviet designers pursued bold experiments, some brilliant, others bizarre. One of the most unusual projects was the T-100Z, a heavy tank prototype developed alongside the famous KV series. It had 3 turrets, one with a 76mm gun, one with a 45mm gun, and the third with a machine gun. The idea was to create a land battleship capable of firing in multiple directions. In theory, it sounded unstoppable. In practice, it was a logistical disaster. The extra turrets made it too heavy and complicated. The crew could barely coordinate. After the Winter War in Finland, Stalin personally ordered the cancellation of multi-turret tanks. Then came the KV-4 and KV-5 super heavy projects, attempts to create tanks with 150mm armor and massive 107mm guns to counter future German designs. Some blueprints envisioned machines weighing 100 tons or more. Construction started, but the German invasion in 1941 halted everything. When the Wehrmacht reached Leningrad, the KV-5 hulls were melted down for steel. The Soviets also experimented with extremely light tanks. The T-60 series inspired a prototype called the T-60S, equipped with a small jet engine to blow compressed air backward, essentially a jet-assisted tank. It didn't work, but the idea was a strange early hint at rocket-assisted propulsion on land. There was also the Antonov A-40, a flying tank. Yes, literally. Engineers attached glider wings to a T-60 light tank, planning to tow it behind a bomber, drop it near the battlefield, release the wings, and drive it into combat. In 1942, they even tested it. Briefly, the plane towing it almost crashed from the drag, and the experiment was abandoned.
Still, for a moment in history, the Soviets tried to make tanks fly. Post-war Soviet designs, like the Object 279, continued this tradition of experimentation. Built in 1959, it featured 4 tracks and a saucer-shaped hull to resist nuclear blasts. It was decades ahead of its time, a Cold War descendant of wartime imagination.
America's forgotten beasts. Across the ocean, the United States took a different route. American industry excelled in mass production, not in eccentricity. Yet the U.S. Army still tested dozens of prototype tanks and vehicles that could have reshaped the battlefield if only they hadn't been too heavy, too expensive, or too late. One of the most ambitious projects was the T-28 Super Heavy Tank. Designed to break through the German Siegfried Line, it weighed 95 tons and was armed with a massive 105mm gun. Its armor was so thick, up to 12 inches in places, that it could withstand direct hits from German 88mm cannons. However, it was too slow, crawling at just 8 miles per hour, and its size made it nearly impossible to transport. Only 2 were built, and both were scrapped after the war. One was later rediscovered in the woods at Fort Belvoir, almost forgotten. The Americans also tried to create a replacement for the Sherman that could rival the German Panthers. The T-20 series was the foundation of this effort, a line of medium tank prototypes with improved suspension, thicker armor, and a more powerful gun. Variants like the T-23 introduced electric transmission systems, while the T-25 and T-26 evolved into what would become the legendary M26 Pershing. These prototypes didn't fight directly, but their DNA shaped post-war American armor. Other prototypes were more exotic. The M6 heavy tank, designed in 1941, was a massive 60-ton vehicle with 2 machine gun turrets and a 76mm main gun. It was too large for American logistics and too complex for mass production. By the time it was ready, the Sherman was already winning battles through numbers, not size. And then there were strange concepts like the Little David mortar, a gigantic 914mm artillery piece meant to demolish fortifications. It was test-fired in Maryland, but never deployed. The gun was so massive that it required its own transport train and could only fire a few shells per day. In the end, aerial bombing made such siege guns obsolete. The Americans also experimented with amphibious and airborne tanks. The M22 Locust, for example, was designed to be dropped by glider for use by airborne troops. It was light and compact, but thinly armored and undergunned. It saw limited use, but its concept laid the groundwork for future air-mobile vehicles. In short, the American philosophy was practical experimentation. Test everything, keep what works, and discard the rest. The U.S. didn't dream of 1,000-ton tanks, but its incremental innovations define the armor of the Cold War. Britain's secret armored experiments. Britain's armored forces went through a painful learning curve during the war. Early tanks like the Matilda and Crusader were underpowered and unreliable. But behind the scenes, British designers were developing experimental machines that might have changed the game if they'd been given a chance. One of the most intriguing was the TOG series, designed by the old gang of World War I engineers who still believed in trench warfare. The TOG-1 and TOG-2 were enormous, nearly 80 tons, with long hulls, heavy armor, and side skirts designed to cross craters in trenches. By the time they were ready, trench warfare was ancient history. The TOG-2 did perform well in tests and were surprisingly mobile for its size, but it was simply outdated. Then came the Churchill Black Prince, a heavily armored variant of the Churchill tank, equipped with a powerful 17-pounder gun. It was meant to counter the Tiger I, but development dragged on so long that by the time it was ready, the new Centurion was already in production, a far superior design. Only 6 prototypes were built. The British also explored extremely fast tanks, like the cruiser Mark 8 Challenger, meant to combine speed with firepower. Unfortunately, its tall silhouette and weak armor made it vulnerable. The Comet, its successor, corrected many flaws, but prototypes like the Challenger showed how trial and error shaped the final wartime designs. There were also unique experimental vehicles, like the Electo, a self-propelled gun that never entered combat, and the Tortoise, a 78-ton assault tank built to breach German fortifications. The Tortoise actually performed well in post-war trials, extremely durable and armed with a 94mm gun, but the war ended before it could prove itself in battle. Britain's secret armored experiments often suffered from slow development and changing requirements. Still, they laid the foundation for the Centurion and the post-war Chieftain, two of the greatest tanks ever built.
Japan's unrealized armor. Japan's armored forces are often overlooked, but during the war, Japanese engineers also attempted several ambitious designs, though most never left the prototype stage. The OI Super Heavy tank was perhaps Japan's most extraordinary. Weighing over 120 tons, it featured multiple turrets and thick armor meant to counter Soviet tanks in Manchuria. Only one prototype was reportedly built, and it was dismantled after tests revealed severe mechanical issues. Japan's industry simply couldn't support such a machine. The bridges, roads, and engines available couldn't handle its weight. Japan also tested amphibious and air-transportable light tanks, like the Type 3 Kachi and Type 4 Katsu, designed for island invasions. The Katsu even carried torpedoes intended to sneak up on ships from the sea. None of these vehicles ever saw real combat, but they demonstrated Japan's creative attempts to adapt armor to naval warfare. Perhaps the strangest Japanese concept was the Type 5 Ho-Ri, a tank destroyer roughly equivalent to the German Jagdtiger. It featured a long 105mm gun and heavy frontal armor. It never reached completion before Japan's surrender. Like many Japanese projects in 1945, it was overtaken by bombing, shortages, and collapse, the legacy of machines that never fought. These forgotten land machines tell a story far deeper than steel and fire. They represent the limits of human ambition, the point where imagination collides with reality. The Mouse, the T-28, the Togue, the KV-5, each of them was born from a belief that bigger or stranger was better. Yet war rarely rewards extravagance. The true revolution came not from the giants, but from the balance, the medium tank that could be built, repaired, and replaced. And yet, without these experiments, progress would have stalled. Every prototype that failed taught engineers something new about armor slopes, suspension systems, transmission designs, or crew ergonomics. The knowledge gained from these so-called failures paved the road to the Cold War and beyond, to the M60, the T-62, the Leopard, the Abrams. In the end, these machines never fired a shot in anger, but they were not useless. They were the missing links in evolution, the silent teachers of the tanks that did fight and win. The battleship's last stand, the monsters that never sailed. In the early years of the war, all major naval powers were still obsessed with one thing: size. The belief was simple: the bigger the ship, the greater its power and prestige. That mindset produced some of the most extraordinary blueprints ever drawn. Nowhere was this obsession more evident than in Nazi Germany. The Kriegsmarine dreamed of a fleet that could rival the Royal Navy and challenge the United States across the Atlantic. Under the Plan Z naval rearmament program, Germany envisioned building a series of massive battleships that would dwarf even the Bismarck. Among them were the H-class battleship series, a line of increasingly monstrous ships that never made it beyond the drafting table. The H-39, for example, was designed to carry 406mm or 16-inch guns and displace around 62,000 tons, larger than any German warship ever built. But the follow-ups were even insane. The H-44, the ultimate fantasy of the series, was projected to displace over 131,000 tons, mount 508mm or 20-inch guns, and require a crew of 2,600 men. To put that into perspective, that's nearly twice the size of the Yamato, the largest battleship ever completed. The H-44 would have been more like a floating fortress than a ship, if it could even stay afloat at all. But these titans were doomed before they began. Germany's shipyards, already stretched thin by the Bismarck and Tirpitz, simply couldn't handle ships of that magnitude. The raw materials, steel, turbines, heavy armor plating, were desperately needed elsewhere. By the time engineers realized this, the aircraft carrier had already proven that even the mightiest battleship could be sunk from hundreds of miles away. The age of the super battleship ended before the H-44's keel was ever laid. The Allies had their own flirtations with madness. The British experimented with the idea of HMS Habakkuk, a colossal aircraft carrier made entirely of pykrete, a frozen mixture of water and wood pulp. The concept came from eccentric inventor Geoffrey Pike, who proposed building unsinkable carriers that could operate in the North Atlantic, immune to torpedoes. The prototype actually worked. It resisted melting even under gunfire. But the logistics were absurd. The full-size Habakkuk would have required 300,000 tons of pykrete, 8,000 tons of insulation, and a dedicated refrigeration system the size of a city. By the time the British Admiralty finished calculating costs, they realized it would take more resources than building 10 real carriers. The project was quietly shelved, but the idea remains one of the most bizarre what-ifs of naval history.
Silent hunters, submarines that were too advanced to fight. Beneath the waves, an equally fierce race was taking place. The submarine had proven itself as one of the deadliest weapons of the war, especially in the hands of the German U-boat arm. But while thousands of conventional U-boats prowled the Atlantic, the Kriegsmarine's engineers were already designing submarines decades ahead of their time. The most famous example is the Type 21 electroboat, a revolutionary design that introduced features we still see in modern submarines: streamlined hulls for submerged speed, snorkels for underwater diesel operation, and vast battery capacity for long submerged runs. But even the Type 21 had precursors, secret prototypes that pushed the boundaries even further. The Type 17, for instance, used an experimental Walter turbine powered by concentrated hydrogen peroxide, allowing bursts of underwater speed up to 25 knots, faster than any submarine in the world. The problem was the fuel itself. Hydrogen peroxide was volatile and prone to explosions, especially when stored for long periods at sea. Test runs ended in several catastrophic failures, and despite the submarine's incredible potential, it never entered full service. One of its test models, U-1407, was later raised by the British after the war and recommissioned as HMS Meteorite. The Royal Navy used it to study air-independent propulsion, laying the groundwork for the future of submarine technology. In a strange twist of fate, the submarine that never saw combat became a key ancestor of the Cold War's silent hunters. Japan had its own submarine ambitions, but theirs were not about stealth. They were about reach. The Imperial Japanese Navy developed the I-400 class, the largest submarines of World War II. These weren't just submarines. They were underwater aircraft carriers. Each could carry 3 Aichi M6A Seiran attack planes in a watertight hangar, launch them via catapult, and then submerge again. The plan was to attack the Panama Canal or U.S. coastal cities, creating chaos far from Japan's shores. 3 I-400s were completed, but they never carried out their mission. By the time they were ready, Japan was already losing the war. The submarines surrendered in 1945 without firing a shot in anger. Ironically, they were later sunk by the U.S. Navy, not in combat, but as target practice, to prevent the Soviets from studying their advanced design. And then there were the truly outlandish concepts, like Germany's Type 29 Seehund mini-submarines or Japan's Kaiten manned torpedoes. The Seehund was a 2-man submarine designed for stealthy coastal attacks, and although a few were used in late 1944-45, the most advanced versions, equipped with sonar-guided torpedoes, never saw action. The Kaiten, meanwhile, was an example of desperate genius, a suicide torpedo piloted by a single man. Thousands volunteered, but few missions succeeded. For all their tragic determination, these human-guided weapons were less about technology and more about the cruel arithmetic of a losing war. Experimental surface ships, beyond the conventional fleet. While submarines and carriers dominated the headlines, naval engineers were still trying to reinvent the surface fleet. Germany again led the charge in radical design. One of the most interesting examples was the Zerstorer 1942C project, a futuristic destroyer intended to mount heavy 150mm guns and experimental high-pressure steam turbines. On paper, it was one of the fastest and most powerful destroyers ever conceived. In practice, the turbines were dangerously unstable and prone to catastrophic failure. Only fragments of the project survived. Meanwhile, the United States Navy was experimenting with hydrofoil ships, vessels that could lift their hulls above the water at high speeds, reducing drag and increasing maneuverability. One prototype, the USS Plainview, began development during the war, but wasn't completed until the 1960s. Still, its conceptual roots trace directly back to World War II. Engineers believed such craft could act as fast attack boats, darting in to deliver torpedo strikes and vanishing before the enemy could react. The concept was sound, but wartime technology simply wasn't ready to make it practical. The British, always pragmatic but imaginative, pursued fast coastal strike craft through the Fairmile and Vosper lines. But deep in their archives were plans for something even more radical: a jet-powered motor torpedo boat. The idea was to use a compact jet engine for propulsion, giving the small vessel blistering speed. Tests were conducted using experimental gas turbine units, but reliability issues, noise, and fuel consumption killed the concept. It was decades before jet-powered naval craft became a reality.
Weapons of the sea, torpedoes, mines, and unseen killers. It wasn't just the ships that were being reimagined. The weapons they carried were evolving just as rapidly. The torpedo, once a simple mechanical weapon, became an object of intense scientific experimentation. Both the Allies and Axis powers developed acoustic homing torpedoes that could track the sound of enemy propellers. Germany's G7S Zongkönig was the most famous, used in the final months of the war. But many advanced variants, capable of differentiating between ship types, never left the lab. The United States experimented with magnetically triggered mines, rocket-assisted depth charges, and even torpedoes guided by television cameras, early attempts at what we would today call smart weapons. In 1944, U.S. engineers at the National Defense Research Committee tested a wire-guided torpedo, the ancestor of modern submarine-launched missiles. The technology worked in principle, but wartime electronics were too unreliable for operational use. Japan, facing blockade and resource shortages, turned to desperate innovation. One of the strangest projects was the Kaiten Type 10, a hybrid between a midget submarine and a guided torpedo. It could carry a pilot for navigation, but switch to automatic mode near the target. The concept was promising, but too complex for mass production, and it never reached combat readiness. Another almost forgotten Japanese invention was the Fukuryu diving mine, a human-operated underwater weapon meant to attack Allied landing craft. Divers carried explosive charges and waited underwater for the enemy to pass overhead. The system was suicidal, inefficient, and never used in combat, but it reflected how wartime desperation could distort even the most advanced technical minds. The legacy of unused naval innovation. In the end, most of these experiments never left their docks. Some were dismantled before they were finished. Others were scrapped quietly after the war, their technologies hidden under layers of post-war secrecy. But their legacy didn't disappear. The Walter turbine, born in the doomed Type XVIII submarine, inspired post-war propulsion system. The I-400 class submarines directly influenced the U.S. Navy's thinking about underwater missile carriers, the spiritual predecessors of nuclear ballistic submarines. Even Britain's bizarre Habakkuk project found echoes in later Cold War research into modular floating platforms. Every one of these unrealized weapons represented a vision, not of the past, but of the future. A future that came too late for the war they were built for, but just in time to shape the wars that followed. The oceans of World War II were not just a battleground, they were a prophecy. And in the blueprints and broken hulls left behind, you can almost hear that future whisper. A world where the sea would no longer be ruled by iron giants, but by silent hunters, machines of precision and intellect, born from the restless dreams of wartime engineers. The spoils of genius, Operation Paperclip, and the global race for ideas. In the immediate aftermath of Germany's surrender, Allied forces moved fast to secure not just territory, but technology. The United States, Britain, and the Soviet Union all launched massive intelligence-gathering missions to capture the Nazi regime's research facilities, aircraft, and scientists. The most famous of these efforts was Operation Paperclip, a covert U.S. program designed to extract German scientists and engineers before the Soviets could reach them. At first glance, the mission seemed purely military. The Americans wanted to understand the advanced weapons Germany had been developing, the jet aircraft, guided missiles, and chemical technologies that had shocked Allied intelligence during the war. But what they discovered went far beyond weapons. They found ideas, revolutionary concepts, decades ahead of their time.
Take the V-2 rocket, for instance. It was the first man-made object to reach the edge of space. Though it was born as a terror weapon, its legacy would transform into something far greater. Under the leadership of Werner von Braun, one of the scientists captured during Paperclip, the V-2's technology became the foundation of the American space program. The rocket's design principles directly inspired the Redstone, Atlas, and eventually Saturn V rockets that carried humans to the moon. It's a haunting irony of history. The same technology used to bomb London paved the way for mankind's first steps on another world. The V-2 never won Germany the war, but it changed the destiny of humanity. The Soviets had their own version of Paperclip, known as Operation Osoaviakhim, in which they relocated more than 2,000 German specialists and their families to the USSR. Among them were engineers who had worked on jet engines, submarines, and radar systems. The designs of many early Soviet jets, including the MiG-9 and MiG-15, bore traces of German technology, from wing aerodynamics to combustion chamber design. Even the Soviet R-1 rocket, a near clone of the V-2, became the stepping stone for the R-7, the launcher that would put Sputnik into orbit in 1957. Once again, a weapon that never achieved its intended victory had reshaped the world in peace. From flying wings to jetliners, the civilian echo of military dreams. Many of the abandoned wartime prototypes were too advanced for military production, but they found new life in the civilian world. Nowhere was this more evident than in aviation. The most striking example came from Germany's Harten HO-229, the jet-powered flying wing that never saw combat. When American engineers examined the captured airframe in 1945, they realized just how revolutionary it was. The Harten brothers' design minimized drag and maximized lift, concepts that would later become standard in stealth aircraft. 2 decades later, engineers at Northrop, particularly Jack Northrop himself, revisited the flying wing idea with the YB-35 and YB-49 bombers. Those too were abandoned due to stability issues and political pressure. But the vision never died. When the U.S. Air Force unveiled the B-2 Spirit stealth bomber in the late 1980s, it was, in essence, a spiritual descendant of the Harten. The lineage is unmistakable. The smooth, blended wings, the radar-absorbing curves, the ghost-like presence in the sky. In a sense, the Harten HO-229 finally took flight 50 years after its time. The same principle of technology migration can be seen in jet propulsion. The first operational jet fighters, Germany's Me-262 and Britain's Gloster Meteor, were only the beginning. Dozens of experimental jet projects, from the U.S. XP-79 flying ram to the Soviet BI-1 rocket fighter, never entered service, but each one contributed to a growing understanding of aerodynamics, heat resistance, and fuel management. After the war, this knowledge spilled into the civilian sector. The de Havilland Comet, the world's first jet airliner, was directly influenced by wartime jet research. Boeing and Douglas engineers drew from military testing data to develop the 707 and DC-8, revolutionizing global travel. The skies that had once been a battlefield became highways of peace, and the technology that was born to destroy now connected continents. The tanks that became blueprints for the Cold War. On the ground, the story was much the same. The end of World War II didn't stop the evolution of armored warfare. It merely shifted its direction. The tanks that never saw combat in 1945 became the ancestors of the Cold War's steel beasts. Germany's E-series, particularly the E-50 and E-75 designs, were intended to replace the Panther and Tiger tanks with standardized modular components. None were completed before the war's end, but their concepts directly influenced post-war armor philosophy. Simplify logistics, use interchangeable parts, and favor sloped armor. When Western engineers examined the blueprints, they recognized the practicality behind the design. The American M48 Patton, the British Centurion, and even the Soviet T-54 all reflected lessons learned from studying these late-war German ideas. The T-54, for instance, embodied the balance of armor, firepower, and mobility that the Germans had been chasing with their E-series. The Americans, meanwhile, adopted the modular maintenance approach in their tank production, a key idea from the E-50 program.
Even more interesting was how experimental propulsion and suspension systems from canceled projects reappeared later. The German hydropneumatic suspension tests, conducted for heavy tank prototypes, re-emerged decades later in advanced tanks like the Swedish Strev 103 and Japan's Type 10. The lineage is technical, but unmistakable, a direct transfer of thinking, even if not of hardware. And it wasn't only German designs that shaped the future. The US had its own prototypes that never saw combat. The T-29 and T-30 heavy tanks, armed with monstrous 105 and 155 millimeter guns, they were designed to counter the rumored German supertanks that never appeared. But their turrets, gun stabilizers, and ballistic computing systems became the foundation of future heavy armor development, leading ultimately to the M103 and influencing NATO design standards well into the 1960s. In short, the battlefield of the future was designed by the ghosts of the past, the machines that never fired a single shot. Naval visions that became modern fleets. If the oceans of World War II were a graveyard of experimental dreams, the Cold War seas became their resurrection. Germany's Type 21 submarine, the first true underwater warship, was the direct ancestor of almost every Cold War submarine design. The Americans used captured boats to build their USS Tang, while the Soviets reverse-engineered several hulls into their Whiskey-class submarines. The idea of a streamlined, battery-heavy, deep-diving sub was no longer science fiction, it was the new standard. Even Japan's abandoned I-400-class submarines left their mark. Their concept, a submersible platform capable of launching aircraft or missiles, inspired post-war research into cruise missile submarines. By the 1950s, the U.S. was experimenting with Regulus missile subs, and by the 1960s, Polaris ballistic missile submarines had become the core of America's nuclear deterrent. The I-400 never attacked the Panama Canal, but its DNA was in the missile silos of the Cold War. The British Habakkuk project, as absurd as it once seemed, even resurfaced conceptually during the 1970s oil crisis, when engineers proposed using Arctic ice islands as floating air bases or radar stations. The technology had improved, but the logic was the same. Use nature's resources as engineering material. From pykrete to nuclear submarines, from silent hunters to global deterrents, the line of inheritance is long, strange, and undeniable. The forgotten engineers, visionaries without a war. Behind every prototype was a team of people, scientists, engineers, mechanics, draftsmen, who poured their lives into machines that were never used. Some were recognized after the war, many were not. Men like Alexander Lippisch, the German aerodynamicist behind the Delta Wing concept, saw their wartime research adopted across the world. Lippisch's theories, developed for rocket interceptors like the Me-163 Comet, became the cornerstone of supersonic jet design. The F-22, F-106, and Mirage series all owe him a debt. Others, like Japan's Hideo Itokawa, who worked on aircraft design during the war, went on to lead Japan's post-war space program. Known later as the father of Japanese rocketry, Itokawa transformed from designing warplanes to building satellites, a perfect symbol of technology's strange redemption. Even within the Soviet Union and the United States, wartime experimenters who had worked in secrecy found new roles as the Cold War unfolded. Their wartime failures
became post-war triumphs. Radar engineers developed weather tracking systems. Torpedo researchers became pioneers of underwater acoustics. Metallurgists, who once crafted armor for tanks, now designed heat shields for spacecraft. The prototypes that failed had taught them something that success rarely could: how to push beyond the limits of the possible.
The philosophical legacy, failure as a foundation. There's something deeply human about these forgotten machines. They remind us that innovation doesn't always march forward in a straight line. History is filled with false starts, dead ends, and near misses. But each failure, each abandoned prototype, adds to the collective knowledge that fuels the next success. The engineers of the 1940s didn't know they were building the future. They were solving immediate wartime problems: how to fly faster, dive deeper, shoot farther. But in doing so, they laid the groundwork for peacetime innovation that would shape the next century. The jet engines that powered the first airliners, the rockets that carried satellites into orbit, the computers that guided missiles and eventually shrank into our pockets, all trace part of their lineage to projects that were once dismissed as impractical or fellaine. If history had gone differently, if the war had lasted another year, or if resources had shifted slightly, perhaps some of these machines would have seen combat. But maybe it's better that they didn't. Maybe their greatest achievement was not in destruction, but in inspiration. Epilogue: The Museum of Ghosts. Today, if you visit the aviation museums in Washington, Munich, or Tokyo, you can still see fragments of these dreams: the rusting fuselage of a Horton flying wing, the half-finished hull of a Type 21 submarine, the test turret of a Tiger prototype. They sit quietly, surrounded by school children and tourists, their once secret stories now told in whispers of admiration and disbelief. These are not just relics of war. They are relics of imagination, proof that even in humanity's darkest hour, creativity refused to die. The prototypes that never fought remind us that invention does not belong to victory or defeat. It belongs to the human spirit, restless, curious, and forever reaching beyond the edge of the possible. As long as we continue to explore, to experiment, to question, those ghosts of steel and fire will never truly fade. They live on, not as weapons of war, but as blueprints for the endless future that began with their failure.